Hello, today I'm in search of machine epsilon. So say we have that simple 2 decimal digit floating point example. So you have 2 decimal digits, a D1 and a D2, and they're separated by a decimal point, so that forms your significand. The S1 is a plus or minus 1 that just gives a sign on the number. It's base 10. The S0 is a sign that would go on the exponent, and then the D0 is a single digit for the exponent. So that means that the exponent can go from -9 to +9. I'm going to say that this is a rounding system, okay? And when I talk about an FLX, so that's a function that floats a given real x and gives it back in the form of d1.d2 with the exponents and the signs. For example, if I have 104 coming in as my real number, well, when I quote-unquote float it, it's going to give me an answer of 1.0 times 10 to the 2. If I come in with 105, it's going to round it up. It's going to give me a 1.1 times 10 to the 2. So in this case, machine epsilon is 0.05, as we will see. So relative error, I'm going to call that rho sub x. Relative error, rho sub x, so that's going to be the float value minus the value, so that would be your absolute error, divided by the true value. So x is your true value. You take the absolute error and divide it by your true value. That's why it's a relative error. I like to rewrite it sometimes in this useful form where you have the floating point of the x value is going to be equal to the x times quantity 1 plus rho x. So sometimes that's useful. No matter what x is, you can say that the absolute value of rho x is going to be less than or equal to machine epsilon. So that's going to be a first view that we take. Then in the example that we had with the float of 105, giving us that 1.1 times 10 to the 2, we can see that that effectively is 110. So we floated it to 110 minus 105 over the true value of 105. So that's 5 over 105. That's very, very close to that machine epsilon. So x, again, comes in as any real number. And when you float it, this is signifying that the set of floating point numbers actually is a finite set. And that's true regardless of how many bits or how many digits you use. At the end of the day, you're always going to have a finite number of floating point values. So the x as a real comes in, it has to go towards the nearest floating point value if it's a rounding system. So I want to steer you towards recognizing what the bound of this relative error is, that it is actually the machine epsilon. Towards that end, I want you to imagine any 5-digit decimal value for our x, our incoming x, any 5-digit decimal value that ends in a 499. And I want to talk about normalizing. So normalizing means that you're going to recast that x in such a way that you have a non-zero first digit, pound, first being non-zero, and then the dollar could be any digit, and then you're going to have an exponent for the 10, any exponent. So your incoming x can be recast in this way without losing any resolution. When I float it, that incoming x, what's going to happen is I lose that 499. The reason I lose the 499 is because it's a rounding system and you're going to round down. So the floated value for x is going to look like this. Now when I go do my relative error, I'm going to have the floated value minus the true value divided by the true value. And the power of normalizing here is apparent because now I can just kind of cancel all the common exponents there. and I end up with just the significands that I can easily combine. And I notice that that this rho, or the relative error here, is actually going to be max when, and you're going to get 0.0499 on the numerator regardless. You can have 0.0499 in the numerator, and the denominator, when it is the smallest, that's when this is going to be max. And that first digit has to, the smallest it can be is a 1. It can't be a 0, but the dollar could be a 0. So when you do that, you end up with pretty much the biggest value you can. And I don't believe you could actually reach the 0.05 because you'd be putting the true value in there. So that's why this is called the machine epsilon. And it sets sort of the maximum boundary for your relative error for doing that floating point operation. So this is from the book. Let's take a look at a couple of particular lines. This means that the round off error of a number will be proportional to its magnitude. So we're talking about, if you remember the way I like to put it, we're talking about here with that sentence, we're talking about absolute error. So here's our absolute error. Yeah, it's proportional to the actual magnitude of the true value. So that's a true statement. Let's take a look at the next statement. In addition, it means that the relative error will have an upper bound. That's what I've been talking about. So the relative error, when I go and take the absolute and divide by the true value, that's going to be that rho x that I talked about earlier. And yeah, that's going to be less than the machine epsilon in 0.05 in the case of the two decimal digit example. So definition number 1 for machine epsilon. For a rounding floating point system, the machine epsilon is 1/2 of the least significant figure of the significand. A little bit cumbersome to say, but the example I showed you with the d1.d2, so that's going to give me an epsilon that's 1/2 of that least significant figure, so it's going to be 0.05. If I happen to add a third digit to the significand, then that would make my epsilon 0.005, or half of that last one. So this means that the rho is going to be less than that epsilon because of the rounding. You're always going to be less than that. This could work for a decimal or binary system, quite frankly. And I want to highlight this least significant figure of the significand. I want to highlight that for a minute. There's a fellow William Kahan from Berkeley. So he's known as the floating point god. So he called this the units in last place, the ULP. If the units in last place is the least significant figure of the significand, this sets epsilon at 1/2 of the ULP if it's a rounding system. A second statement in the book says the machine epsilon can also be thought of as the smallest number that when added to 1 gives a number greater than 1. That's going to lead to a different definition. The machine epsilon is the 1 and the least significant figure of the significand. That's the only way that you can get, that's the minimal way that you can get 1 plus epsilon not being equal to 1 in any floating point system. So it has to be actually a full ULP in this definition. The two definitions are really not compatible. Had we tweaked the definition 1 to be for a truncating floating point system, then yeah, they would have been the same. But for our system that we're looking at in definition 1, we were considering a rounding system. Let's take a look at our floating point example, the IEEE 64 double float. You have 64 bits. You have M, a mantissa, that is an unsigned 52-bit number that's stored. You have an exponent e, that's a biased exponent, that's 11 bits, so 52 plus 11 is 63, and then the last bit is used to hold the sign on the number. So you have S as a 0 or a 1, 0 meaning it's a positive number, 1 meaning it's a negative number, because it is the exponent on this -1 prefactor. The E is biased, so you take whatever 11-bit number you have, 0 to 2047, and then you subtract off the 1023. So that's the power on our binary system, so it's the power of 2. And then the mantissa is an unsigned 52-bit number, and I've shown it here in such a way that you take that 52-bit number and divide by 2 to the 52, and that will give you a fraction that you add to a 1. The 1 is hidden, and it's not stored, but it's understood to be there. So this seems to be a rounding system, and earlier I said, hey, we're going to revisit that at a later date. We're doing that now. It is a rounding system. And when I say float, the float function, the flx, then we're going to take an incoming x and we're going to float it. We're going to declare a mantissa for it, a 52-bit mantissa. We're going to declare an exponent and then a signed bit. If we come in and look at a very simple, exactly 1 coming in as our x, then we're going to have a 0 mantissa. Remember that you have that hidden 1. And since it's 1, we're going to have an effective exponent of 0. So that means that my e that would be stored is actually 1023. So that after it's biased, it will give me 2 to the 0. Let's keep everything the same and just tweak the mantissa from 0 to 1. That's the smallest mantissa that you could possibly have. And you know what? That is how the machine Epsilon was defined, a definition 2 type of thing for the binary system. When you calculate the 2 to the -52, that's about 2.2 times 10 to the -16, and that's how you see it over here when you print out the 1 added with the epsilon. So remember that leading 1 is not really stored in the double float. It's just something that you have to remember that is there and sort of hidden. I added a fun one here where I just started with 1 and started adding digits 2, 3, 4, 5, 6, 7, 8, 9, and then just repeating. That way it kind of helped me keep track of how many digits I was proclaiming there. So I added that as a fun one, and the mantissa, corresponding mantissa looks like that. What I'd like to show now is taking those mantissas and changing their representation to hex. So a lot of times I'll do that because it gives me a better feel for what the real value is, since we're really storing binary. This last one here is really good because it's a pretty high number, and you have data in each of the 13 nibbles that you have in the 52 bits. So you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 nibbles. So yeah, we've got data in every nibble. Here I wanted to get you a little bit more comfortable dealing with hex. So I've shown the significand now with the leading 1, and then I have 13 hex bits, and that's a nice convenient way to do that. And from what I had in the previous slide, I was showing the x values in decimal, as I've shown here, and now I'm showing the significand actually in hex format, and even the one that had 1 plus epsilon, you've got the 1 in that final ULP there. And then the kind of the fun one with all the digits ends up looking like that. And I can carry that even further and show the mantissa or the significand in a truly binary form, 1 dot, and then have the 52 bits and show that as base 2. So I can continue this, and these are actually equal. I had the 16 base version. Now I'm showing the binary or the base 2 version right below, and then you can see here very clearly the ULP right there. And then you have the fun one where you have those 13 hex bits we saw earlier. Again, you see that the machine epsilon, the 2 to the minus 252, that is that spot right there. That is the ULP. So it is a definition 2 machine epsilon. The way the floating point kind of plays out, let's take our fun example where we have those recurring digits and we remember the hex value of it. Let's kind of see where this goes. You can see that the hidden 1 is there, hidden 1, and then the hex mantissa that we had before started with a 3C and ends with an FB. So you can see the 3 right there. You can see the C, and then on the end, you can going backwards, you see the B there, and then you see the F. And remember that your exponent here is going to be 1023. 1023 is 3FF, as you can see right here. 3FF, 1023, and the binary version of that is F there, and then you have a 1, 1 there. And then taking that mantissa with the binary representation, you can see easily how that maps out. The sign is 0 here since it's a positive number. So here's what the 64 bits would look like. The mantissa are the mantissa bits going to your low 52 bits. So you have, this would be your B down here, your F goes here, and then on the high end you've got 3 and Charlie. So there's your 3 and there's your Charlie. So those fill up full nibbles. And then the 11 bits of the exponent with the 3FF, it's not going to fill the full nibble over here. You're only going to have 3 bits because it's 11 bits. So you're going to have a 3FF there, and then the sign bit is all the way at the top. So that's how it's stored. And remember that your 1 is not shown in here, not represented. So here I've just restated that fun example where it had the digits sort of going through that pattern, and I had the fun floating point result of that. And what I was thinking is, what if I had continued on the madness of just continuing to add those repeating digits, and I had a whole bunch of them, many more than I really needed, because really what I want to do is I want to add 3 more nibbles. I've got 52 bits here on the mantissa for double float, and I just thought, hey, I want to add 3 more nibbles. So I'm going to look at taking this value and giving a 64-bit mantissa representation of that, and that's what I did. So it ends up looking like after the FB that we had before, I continue with a 7-1A in terms of the mantissa. And I've noted the mantissa is M64 here to differentiate it from the double float mantissa of M52. So the point is I'm trying to increase the resolution and then look at, well, what is that going to do for me once I do the floating point operation? So let's look at that. I'm going to state the relative error for that fun one. So let's say that the X is a whole bunch of stuff there, just those repeating values. So it's going to have the same exponent. So normalized, this value sort of normalized, like I say, it's approximately equal to that. As I was saying, I'm adding 3 more nibbles to represent what the next few decimal digits would give me be equivalent of. So I'm adding the 3 more nibbles there, the 7-1A, that just carries on. Now I take that as the true value, and then of course once I float it, the 7-1A is going to go away because I'm going to round it. It's going to be rounding down, so I'm going to get that FB being the last digits. Exponent's going to stay the same. Now when I do the now when I look at the relative error, I put in the floated value minus the true value divided by the true value. That's what we've done a number of times. And now, remember, like we did in the decimal, I could just kind of kill these exponents and look at it from an absolute perspective. And what's going to happen is everything up to the FB is going to, including the FB, is going to get zeroed out when I subtract them. So the numerator is going to have the 13 zeros after the decimal place. And then I'm going to have the 7-1A. And then again, I'm going to divide by the true value. So that would be the relative error. And I could calculate this. I could carry this calculation out, even though it's in base 16. I could calculate it, come up with a value. Before I do that, I'd like to set a bound on what the relative error might be. So let's say I have a normalized true value for x as being 1, followed by 13 zeros, and 7ff, so that's in hex base, and I've got any exponent. When I float this value, I'm going to end up with a 1, followed by all zeros, base 16, and I'm going to have the same exponent. And I've set it up this way so that 7ff is actually the max I can have without having to make that last bit a 1. So I'm going to round down to that last bit staying, or last nibble staying as a 0. So that's the floating point value of this true value. So now when I do the relative error, I do the floating point value here, and I subtract off the true value, and then I divide by the true value. And as I was showing you before, the exponents just kind of go away. They get killed, and we're left with just the significans shown in base 16. And if you notice, the 1 followed by the zeros there, are going to subtract off the 1 followed by the zeros up to this point. And we're just going to have that 7 fox way out there. And then we're going to divide by the true value and it's just a significand that's left, the 1 followed by the zeros and the 7 fox. Well, that is, because this 7 fox is so far out there, the denominator here is approximately 1. And if you notice, the 7 fox there is approximately the same as 800 hex in that location. Right there, it's just 1 bit off. Had I put 800 here to begin with, then that would have rounded it up and that would have changed to a 1. But that's why I kept it at 7ff, but it's pretty close to that. And when I bring in what the definition of epsilon is, remember epsilon has a 1 in that last nibble. So you can see, remember this is hex here. You can see that 800 in that position, that is 1/2 of that. So that means that this is approximately equal to epsilon over 2, and that's the upper bound. So this is as high as it can go. And this is a definition 2 epsilon, remember. That's as high as that relative error can go. In MATLAB, the high precision mathematics is handled with the VPA. It's part of the symbolic toolbox. So I'm going to declare a symbol as that fun one. 1, 2, 3, 4, 5, 6, 7, 8, 9. No, that's 10 digits. 20. That's 30. And I think by default the VPA is accurate to 32 decimal digits. So I'm going to stop there. And then I'm going to declare XVPA as a VPA. So that's variable precision arithmetic, I think is what that stands for. And it wants a symbol. So I'll give it to you right there. Okay, so that's my XVPA. It's a high resolution, something I can do calculations with. High resolution representation of that. And I want to go ahead and get a double float of that. I can do that with the double function, XVPA, like that. And I have a function in my workspace here, float64b, and that will give me a structure, float64b, of the double, and we should see some familiar things here, so I'll let that run. Sine 0 exponent is 1023, and there's the decimal mantissa that I showed you a while back. I can show more, float64b, show more, the function's called. I give it that this is the structure representing the double. It's rounded and round, so that's the float operation right there. When I do a double of that VPA variable, that is the float operation. Then I'm taking that floating point value and breaking it apart with that. And now I'm going to show you what it looks like. So you have the exponent, the mantissa, that's the same string we had before. And here I've shown the hex and binary versions of it with the leading one shown with the mantissa that follows. So that's the floated value that we've got there for the x double. So that's what that is. I could use my hexaphi VPA function on the VPA value. See, hexaphi VPA, yep. That on the XVPA version. Let's see what that looks like. And that's just going to show the mantissa with the extra 7.1a there. And then there's the bitify VPA of XVPA. And that's going to show, I think it gives 65 bits, and does show the leading one. It just doesn't put a decimal in there. So I think the 3 picks up there, the 3 Charlie is there. And I think the 7.1a, there's the A, there's the 1, and there's the 7 from that. So that's the high res bits and pieces, bits and nibbles, how about that? That's the high res bits and nibbles, and these are the low res or floated bits and nibbles. What I thought about now is seeing, well, if I could use the VPA arithmetic to actually calculate relative error. Let's see what we get. So if I have relative error, let me pick up right here. So I'm going to do an absolute value of x VPA minus this bit right in here. All of this is a symbolic version of the floated value. Let's figure that out. So I've got 1 plus the mantissa divided by 2 to the 52. 1 plus the mantissa divided by 2 to the 52. So that takes care of the significand. And then I have the exponent minus 1023, and then I'm using that to raise the 2 raised to that power. And then I'm doing a VPA of all that. So that's the floated value right there. And then the true value is just VPA, XVPA. True value in the denominator is XVPA. And then I doubled the result. So that should be my relative error. Let's see what it is. So it's roughly 8 times 10 to the 17th. And one thing I've been really focusing on myself is to take that relative error and divide by the epsilon. Remember, epsilon in MATLAB is the 2.2 times 10 to the 16th. That's that unit in last place. So if I do x relative error divided by eps, that's 0.36 roughly. Remember, I had bounded the relative error in an earlier slide showing you that it has to be less than epsilon divided by 2. Well, if you take the relative error and divide by epsilon, then it is bounded by 1/2. So we are pretty high here with this particular example of relative error. And that relative error, just to kind of recap, that relative error came from the original real value of that getting floated right here. I put together a comprehensive function that it's called precision test that receives a symbol or a string, creates a symbol, does a VPA, and then it floats that VPA, and then it breaks that VPA apart into the structure pieces. And then right away, it can go ahead and calculate the relative error using that format I showed you earlier, where it does the VPA of the floated pieces. And then I can get what I call locally here EPS fraction, and that's going to be that relative error divided by EPS. And then I could do some pretty print statements to show the VPA as a symbol and also as character string. And then I can show the bitified values, both raw and dotted. And then I can show the double and then show the pieces of the double. So this is a nice kind of comprehensive function. The function returns EPS frac, and the reason I do that is I want to actually set myself up to run precision test a bunch of times and see what my highest EPS frac might be. So in that spirit, let's run precision test on our favorite example. It prints out the VPA, the 32-digit representation. It shows that X relative we had before, and then the EPS frac is 0.36 that we had before, and then it does the VPA bitified, the raw without the decimal, the bitified with the decimal dot between them, and then it does the hexify raw, and then it shows it with the leading one and the decimal. Here's the double representation, and here's the hex of the double. And then remember, we had this in our presentation where we had a trailing FB that was the end of the floating point representation, and then we carried on with the 7.1a in the VPA version, the high-res version. And the same thing can be said between the bitified VPA and the bitified double. I wanted to show you the example that gives me the highest EPS frac that I've found so far. Precision test, right there, so it's a 256 and a whole bunch of digits there. Let's see what that gives me. Okay, so the EPS frac, if you will, is 0.4998. So that's as high as I've gotten so far. Let's look at what the hexified VPA looks like. So it is 1, and then towards the end we have a 43D800. So that 800 is going to want to round up. Those last three nibbles are going to want to round up when it gets floated, and the 43D800 rounds to a 43E. So the D rounds up to an E because of the 800. So very, very close to that 1/2 limit that we talked about earlier. So in summary, our machine Epsilon has been found. If we have a true value X and then we turn around and float it, the absolute error is going to be the floated value minus the true value, and then we take that absolute error and divide by the true value. That's going to give us our relative error. And the relative error has a bound intimately related to how the machine Epsilon is defined. Let's talk about the first definition of machine Epsilon. And we're talking about rounding system, a rounding floating point system. So in that first definition, our Epsilon is defined as 1/2 the units in last place, or 1/2 of the least significant figure in the significand. So when that's the case, the bound on relative error is going to be less than that definition of machine epsilon. A second definition of machine epsilon is the one we find when we're dealing with a binary floating point. In that situation, epsilon is defined as that full units in last place, and that's the only way you can get epsilon when you add it to 1 to not be equal to 1. And we're still talking about a rounding system, so what that means is that the bound on relative error is going to be less than 1/2 of that second epsilon. So theoretically, we discussed this using base 16, and then we experimentally showed this using MATLAB, the MATLAB VPA function. What would be nice is to go back and look at the theoretical hexadecimal representations of this as well. But that's all for today. I hope you enjoyed it.